Folks, in the previous section we introduced the topic of multivariate functions, that is, functions who have several independent variables. And we now want to begin laying the groundwork to do calculus with these multivariate functions. And of course we can't do calculus without the idea of limits. So that's what we're jumping into here in section 15.2. We want to explore the notion of limits of multivariate functions. In my opinion, this is one of the first sections where the tools we're going to utilize in this section are going to drastically differ from the set of tools that we used in Calc 1 when we introduced limits there. So pay attention to these examples because I think there's some challenging ones ahead. But before we get there, let's go ahead and do a quick review. Here we have a limit. This is kind of a classic Calculus 1 problem, and let's show that this limit here does not exist. So in order to answer this question, we have to remind ourselves of the definition of the absolute value. Reminder that the absolute value of a is a piecewise function, and it's equal to a if a is greater than or equal to 0, and it's equal to negative a if a is less than 0. And so let's go ahead and tackle this limit problem. We've got the limit as x is approaching 1 of the absolute value of x minus 1 all over x minus 1. And notice that the sign on the argument inside the absolute value, that x minus 1 factor, if I plug in numbers that are just to the right of 1, that argument's always going to be positive. And if I plug in numbers that are just to the left of 1, like 0.9, that argument's going to be negative. What's the problem? In order to simplify the absolute value sign, I have to determine whether the argument's always positive or always negative. And if all I know about x is that it's approaching 1, I can't make that distinction. So what I'm going to have to do is assign a direction of approach here. So let's start off by saying x is approaching 1 from the right. If we do that, then we can argue that this expression inside the absolute value here is always positive. Why is that? Because x is approaching 1 from the right, so that's numbers like 1.1 or 1.002 or something like that. When I subtract 1 from that, I still have an expression that's positive. And so what we can do is say that that's just equal to x minus 1 all over x minus 1, where I evaluated the absolute value based on the fact that I knew the argument, the stuff inside of it, was always going to be positive. And so notice we can now simplify this greatly because we can say, hey, this function right here is equivalent to the function 1 everywhere except for where x equals 1, and then we can apply the direct substitution property from Calc 1 and then say that that limit is 1. Well, that's only checking the limit from one direction, and we wanted to find this proper limit from both directions, so now we need to check the other direction here. So we would check the limit as x approaches 1 from the left of the absolute value of x minus 1 all over x minus 1. That's equal to the limit as x approaches 1 from the left, and this is where it gets a little bit different. The argument, the stuff inside this absolute value, x minus 1, if x values are approaching 1 but from the left, that expression inside the absolute value is always going to be negative. How do we take the absolute value of a negative expression? Well, our rule says if the expression is negative, change the sign on it. So here I am, I'm going to take the absolute value of this expression that's always negative, and you take the absolute value of an expression that's always negative by changing the sign on it. That forces it to obey the absolute value rule. This looks very similar to what we had in the line above it, but now we can go ahead and replace this function right here with a function that agrees with it everywhere except where x equals 1 potentially. And so this is equivalent to the function negative 1, and the limit of a constant we know is just the constant. So here we see that the left-hand limit, which we just evaluated here, that we could call this the left-hand limit, does not equal the right-hand limit. So this limit, as x approaches 1 of the absolute value of x minus 1 all over x minus 1, does not exist. And so without going into too much detail, I want to say that when we did this limit in Calculus 1, we only had two potential directions to check, an approach from the right, which you saw here, and an approach from the left, and that's all we had to check. When we do limits of multivariate functions, that is not the case. And in fact, there would be infinitely many directions and paths and types of approaches that we could take towards a limiting value that we'd have to check, which is in a way impossible. So some of our tricks from Calc 1 will not apply here. To get you ready for this and to show you a problem that we're going to work in class, I want you to compare these two multivariate functions, f and g. Okay? Both of these functions just involve x's and y's and some squaring and some multiplication and some addition. Neither of these functions is defined at 0, 0. So I cannot plug 0, 0 into either of these two functions. It turns out, though, that one of these functions is well behaved around the ordered pair 0, 0, and one of them is not. Meaning it's possible to compute the limit as, now here we're going to see this notation, not as, say, as individual x value is approaching 1, but as an ordered pair is approaching the ordered pair 0, 0. That's how we're going to look at these limits in this section. So I don't think it's entirely clear which of these two limits is going to end up existing. And it turns out that the limit of f of x, y, does not exist at the point, at the origin, at 0, 0. Whereas the limit of g of x, y does exist at the origin, and it turns out to be 0. And I don't think there's anything you can see from this right off the bat that would let you notice that. Now, we could go ahead and explore the graphs, and that's going to give us a little bit of insight. So let's go ahead and check those. So if you click that first GeoGebra link, it pulls up the graph of f of x, y, which we said the limit isn't going to exist at 0, 0. Something wonky is happening there, and it will be impossible to give a description of the behavior of the function near that point. And what we see here is a really interesting situation in this graph. So I'm rotating it about for you to take a look at, and I encourage you to click the link and explore it yourself. We see, for instance, if I were to approach the ordered pair 0, 0, there's that origin. If I were to approach, see my mouse here, my mouse is moving along a particular line. And if I approach along a particular line, this one right here, it looks like the z values are always getting closer and closer to z equals 0. So along this direction of approach, we would think that the limit might be 0. Notice if I were to come along the line y equals x, so let's see here, that's, let me get this in the correct orientation, along this line right here where y is equal to x. So imagine me putting a line where my mouse is moving as I go across this. It would look like the limit was 1. So at this point, we've shown that the limit in one direction along this line right here appears to be 0, and the limit along this line right here appears to be 1, though we've proven neither of those. And in fact, notice that I could come in along some other path here, many other paths, and get many other limit values. So the limit, as we approach the origin in our domain, as our points approach the order pair 0, 0, doesn't exist in this case. So I encourage you to take a few minutes to explore this graph and think about this idea of what would we expect the z value to be as the x and y coordinates approach 0, 0. Convince yourself that there is no single value that z would approach. And let's look at the other graph now. So here I've clicked the link to show the graph of g of x, y, which is this function right here. And it's a complicated looking function. But what we see here is, unlike in the last example, is I approach the domain value 0, 0, which is the origin, regardless of the direction that I approach 0, 0, that ordered pair, my z values always seem to be approaching 0. Let's check that. So let's see here. Here's our positive x-axis. Here's our positive y-axis. If I were to approach along the y-axis, for instance, my z values seem to always be nearing 0. Same thing as if I approached along the x-axis here. My z values always seem to be approaching 0. And I could take a non-origin approach, like I could move along the line, let's see here. Here would be the line y equals x. And so this is my mouse tracing the line y equals x. Here's y, so the line y equals x is this 45-degree line here. If I were to move along it, my z values would start out very negative, but as I get closer and closer to the ordered pair 0, 0, it appears to be approaching a z-value of 0. Now, here's the rub, folks. I've been talking about taking lines as approaches towards the origin, but in fact, we could take any sort of path. So I could take, follow my mouse, I could take maybe a spiral path in towards the origin. That's one possible path that I would have to take into account. Or I could maybe take a parabolic path in towards the origin. And so there's many, many different routes. So if I did this spiral path in towards the origin, notice I'm getting many different z-values as I get closer and closer to the origin, but those z-values are approaching a z-value of 0 there. And so because this works for all possible paths to approach the origin, the ordered pair 0, 0, for all possible paths, regardless of how I do that, my z-values always seem to be approaching 0. That's what enables us to conclude, in this example here, that the limit of g of x as we approach the origin is 0, where the limit of f of xy as we approach the origin didn't exist because that was direction dependent. We'll pick this up in the next video, folks.